It is a pleasure to kick off the science component of this talk, and talking a little bit about the work from our team on enabling electric vehicle adoption through fast charging batteries. This work was shepherded by myself and Professor Bruce Dunn, who's waving his hand right there. This has been a completely collaborative effort, and I really need to say that Bruce and I just talk, and the people who were on the ground and did all this work is a phenomenal set of students, many of whom are also at that table and can raise your hands. Susan, Ju, Jackie Yu, McKenna White, Becca McAlpin, and Quen Nguyen. So thank you to the people who really do the work at this university. Okay, so we're talking about electric vehicle adoption. I'm not actually going to talk about electric vehicles. I'm going to talk about batteries, but I want to just set the stage. What is the need for speed? Okay, so in a typical slow electric charger, a level 1 or a level 2 charger, it can take you between 4 hours and 2 days to charge an electric vehicle. If you have bought a Tesla, I think I'll just leave it at that, you can potentially charge in as little as 30 minutes with a level 3 charger. But this is competing with gasoline, where you can fill up a car in 2 to 3 minutes. And so obviously there's a real time disadvantage to electric vehicles. If one could get charging down to about 10 minutes, it would be highly competitive with electric vehicles, and there would be no real disadvantage time-wise. So what are the impacts if we could go from level 1, level 2 Tesla to what people call XFC, or extremely fast charging? So the advantages are huge. In the first place, we could actually lower the carbon footprint of batteries in general, because cars could have a lot smaller battery packs, because range anxiety wouldn't be so high. It would be easy to recharge. And so you could just pull up and recharge your batteries. You wouldn't need this huge amount of raw resources to go into the batteries of cars. Right now, things like high-use vehicles like buses and rideshare cars are not electrified because they can't take the time out of service to recharge. And so you could have electrification of those high-use vehicles. There's a huge social equity issue here. California has stated in its climate goals that all vehicles are going to be clean air vehicles by 2035. And right now, if you live in an apartment and park on the street, that's a huge personal impediment to owning an electric vehicle because charging times are so slow. And finally, we waste a lot of time waiting for our cars to charge, so we could just increase productivity. Okay, so I'm going to talk about some materials. We are material scientists, so I'm going to talk about materials for fast charging batteries. To do that, I need to really fast tell you how a battery works, because I'm assuming you do not all know. So batteries had 2 halves. They are called the cathode. I hate this pointer. The cathode and the anode, and they are separated by a liquid electrolyte. If you break your battery, the liquid is the electrolyte that conducts lithium ions. In this material, the cathode is in this battery. The cathode is the material that is stable with lithium in it. The little circles with pluses are lithium ions. Anytime you see a circle with a plus, that's lithium. When you charge your battery, you rip an electron out of the battery, out of the cathode, and stick it in the anode, and that forces a lithium ion also, okay, I can't make this move, also to move between the cathode and the anode. If you then take your fully charged battery where you forced all the lithium into the anode, if you connect a wire, that wire can be, those electrons can be used to power your device, and the lithium will diffuse back. And if you ask what limits the speed of this charging process, it is the diffusion of those lithium ions in the solid state, in the anode and the cathode. Turns out that there are somewhat better options for anodes than there are for cathodes, and so this talk is focusing on materials for fast charging cathodes. When we talk about batteries, we talk about 2 things. We talk about energy density and power density. Energy density is how much lithium you can put in the material. It is an intrinsic materials property. Power density is how fast you can take that lithium in and out. And so we are focusing on creating high power devices. So if you look at the current technology, there's a million different kinds of batteries out there. They're all the same inside. They have for the faster charging systems, they have 3 different possible cathodes, and 2 of them are almost the same. There's a lithium nickel cobalt aluminum oxide called NCA, a lithium nickel manganese cobalt oxide called NMC, and a lithium iron phosphate. So these 2 are very similar. They have, they're both pretty high energy systems. They are high voltage. We're going to talk about capacity and voltage. The capacity times the voltage is the energy that you store. So you need high capacity and high voltage. So these are high voltage systems. They have low resistance. That makes them pretty easy to charge fast, but they contain cobalt and they're really expensive. And they're the reason that electric vehicles are so expensive. A lot of low-cost vehicles from China are currently using lithium iron phosphate. This has no cobalt. It's a much lower energy material, a much cheaper material, but it is a much lower voltage material, only 3 volts, and that means it is a much lower total energy stored material. It also has horribly poor resistance, and so you have to coat the whole thing with carbon. Okay, so what are we going to do? We are moving to a next generation material called lithium vanadium fluorophosphate. I'm just going to call it LVPF. And this is an alternative cobalt-free cathode. It has a much higher, it is very similar to lithium iron phosphate. Not quite as cheap because vanadium is not as cheap as iron, but it is much higher voltage. Otherwise, it has many of the same properties as lithium iron phosphate. So it's a great, interesting material, except that in the bulk, it is not fast at all. So how do we make this a fast charging material? Well, Bruce and I have spent the last 2 decades turning slow battery materials into fast battery materials. And we know how to do this. So the first thing is you have to go from big chunks of material to little tiny chunks of material. Unfortunately, that's not enough because if you make little tiny chunks of material, you can't get electricity through them. And so instead of just making little tiny chunks, what we make is a nanoporous network of that material so that the intrinsic size is small. Lithium ions don't have to move very far, but the whole network is electrically interconnected, and you have these holes for all the liquid electrolyte to flow through. Okay, so we have developed methods to make this LVPF by low-cost solution phase methods where we take a polymer and use this to, if we just go back here, we need to make these holes. So we need a method to make these holes. And the method that we use is we take a polymer and we co-assemble it with precursors to the material. We do that in solution. So we just simply mix things, let them gel, and then heat them. We degrade the polymer and it leaves behind holes. Okay, so we did this actually a little bit ago. We made nanoporous lithium vanadium fluorophosphate. This is an electron micrograph image. You can see all the little holes. We can characterize it. It's good quality material. And it charges quite quickly. So for those of you who are battery aficionados, this is the raw data. Most of you just want to look at graphs like this one. So on the y-axis, we have capacity. And what we do is we cycle our material faster and faster and see how much of the capacity it retains. So we use this notation 1C. 1C means we charge in 1 hour. 10C would be 1/10 of an hour or 6 minutes. 30C would be 1/30th of an hour or 2 minutes. And you can see that this material does not lose much capacity as you charge it faster and faster. That's all great, except that this is made with a template that is completely non-scalable and impractical. It's made with little tiny spheres of plastic that are made in a very tiny batch method. And the result is that although this material shows exciting performance, it could never be used in a practical battery. So enter this program. We said we're going to come up with a way to actually make this material using scalable synthetic methods. And so to do that, we need a really low-cost way to put holes in it. What we use is literally soap. This polymer has a water-loving block in blue, a water-hating block in red. It makes little tiny spheres in water. That's the soap spheres that clean the grease out of your clothing. It's actually used in laundry detergent. It's that cheap. Those spheres are too little to actually make a good battery material, and so we developed ways to add extra of the water-hating polymer in red down at the bottom and make great big spheres. And we said, we're going to replace our really expensive plastic spheres with this very low-cost soap. Okay, so we set out to do this, and we started making materials, and they were horrendous. So our initial materials had no nice nanoscale structure, and when we went from a 1-hour charge to a 2-minute charge, we lost all of our capacity. So we said, okay, how do we optimize this? And so over the course of this program, the folks who have been involved here have done a huge amount of work developing conditions where they could make really homogeneous nanoscale materials through low-cost methods. And in particularly, they developed a basically hot water vapor annealing method that could produce homogeneous nanoporous materials. And if you look at this picture, the key thing is the nanoscale network is completely interconnected. And so you can actually get electricity out and get lithium into all of the material. I said these materials are poor conductors, and as a result, you have to build in an integrative conductive carbon network around the material. And so the students also work to develop methods to build that network. So the network is formed dynamically as you crystallize the material. You put in carbon precursors, and so they optimize the methods to maximize the amount. I have no cursor. Oh. There, to optimize the amount of carbon. This is a method where we just burn off the carbon, so the bigger the drop, the more carbon we had initially. And what we find is when we put more carbon to make the material more conductive, it charges faster. So the red has more carbon than the black. We keep more capacity at higher rates. We then optimized literally everything about the batteries. I could show you graphs where we look at how fast it charges for every single one of these, but you would probably die of boredom. So I'm just going to make the list of the amazing set of work that Jackie and McKenna did, looking at slurry composition, the type of conductive carbon that they added, the way they formulated the slurry, literally the way they mixed the slurry, the electrolyte, the particle size, the cycling conditions. And the result was a really optimized set of batteries. So in the fastest charging protocols, we use what's called a constant current, constant voltage protocol, where we charge rapidly up to about 80% of the state of charge in 2 minutes, and then we trickle charge the rest of the capacity. That gives you the most capacity. And this is just an overall summary of what we've been able to accomplish. This is data for our low-cost, scalable lithium vanadium fluorophosphate in red. I am comparing it to lithium iron phosphate, which is the other low-cost alternative. And what you can see is that the capacity retention of the red material is infinitely better than the lithium iron phosphate. And I also just want to remind you, this is capacity, number of electrons. And that doesn't take into account the fact that the lithium iron phosphate is a 3-volt battery, and our lithium vanadium fluorophosphate is a 4-volt battery. Okay, so let me conclude. I hope that I've showed you that over the course of this project, we have been able to develop methods to produce nanoporous lithium vanadium fluorophosphate in a low-cost solution-based method with really low-cost polymer templates. We've optimized the nanoscale structure. We've optimized the carbon content. We've optimized the way to build these into batteries. And I think the net take-home message is that LVPF is a really interesting alternative to lithium iron phosphate that can show fast charging, is a cobalt-free system, and has significantly higher voltage capabilities than lithium iron phosphate. So I just want to end by thanking this program. We don't always get to take research from, oh, here's just the first very proof of principle, to really developing it into a more practical system. And so we really appreciate the opportunity to do that.